Good morning again, everyone. Today we are going to talk about and hopefully finish weaving transformation. I mean, if we can finish it in 2 hours today, we will have our 1 hour Thursday for like midterm review because we are going to have our midterm exam this Sunday at 6 p.m. So if you have any questions before the midterm, I'll be happy to answer them. And also, I mean, if you cannot finish weaving transformations today and we continue on Thursday, I may conduct an office hour on Friday. Again, you'll have some time to ask your questions if you have any. Okay, so let's go ahead and start. In weaving transformations, I talked about camera transformation last time, in which our goal was to convert from the world coordinate system to camera coordinate system. And the main reason is to make the subsequent, upcoming projections, like projection transformation, easier to compute. Because just think about ray tracing. If the camera was at 0, 0, 0 and the gaze is 0, 0, minus 1, that vector minus z-axis, all the calculations will be very easy. I mean, those ray generation, finding the pixel coordinates on the image window, that will be really easy. And in order to make those computations easy also for projection transformation, the camera transformation, its main purpose is to change the coordinate system so that camera position becomes the new origin and camera looking direction becomes the new minus z-axis. That's the camera transformation. And then we are going to see projection transformation and viewport transformation. This is basically converting normalized coordinates to image pixel coordinates. This is what viewport transformation is about. And the main transformation that performs the three-dimensional coordinate to image window coordinate, that's the projection transformation, and that's a very critical component of forward rendering pipeline, which we have started seeing parts of it, like starting with modeling transformations. So here, this slide also try to summarize just try to explain why we are doing these things. Why are we doing viewing transformation? So in ray tracing, which is also called it's a backward rendering algorithm. We had a camera here. We had our eye position, and we were shooting rays in the reverse direction of the light rays. Actually, the light rays are coming towards our eye, but we are back tracing the light rays. That's why it's called backward rendering. So starting from the eye position and given a pixel ij value like this, we shot our rays, and then we shot our rays. The number of rays was equal to the number of pixels on our image window, and for each ray we tried to figure out what color that ray is going to be so that we can set this pixel value. So each pixel is computed its color by shooting rays through it and finding intersection with the objects, computing the color, whether it's in shadow, whether there are reflections. So it's a really detailed but highly parallelizable, as you can see, algorithm. In forward rendering, the algorithm is going to be like this. It's called forward rendering because we're going to now start the light rays as if they're bound at the point we'll start tracing the light ray as if just as they bounce off the surface of the objects. And but the question we are going to be asking is, for each vertex of a primitive, instead of generating, because if you're going to start every surface point, if you're going to consider all the surface points, there are infinitely many of them. It will be a very inefficient algorithm to try to project many points on the surface. So what we do is, the algorithm works like this. Given a world coordinate vertex here, like this XYZ, our goal will be to ask which pixel does this vertex contribute to or project onto. So we'll try to answer this question. And given the original XYZ coordinates of this cube, the first step will be to perform modeling transformations on it. For example, this cube may be made smaller, it may be rotated, it may be translated. So these XYZ values we have here may not be the original, the world coordinate of this vertex XYZ after modeling transformations may not be the same as that we have in the file for this cube object. So the first modeling transformations build the scene, find the coordinates of these vertices in the world coordinate system. Then our goal will be to get this world coordinate system XYZ to some kind of an image coordinate system on the image, okay, or on this is also called viewport. So this window is our viewport. Actually, the viewport is the one on the screen, on the image, but we call this image window. Let's keep calling it image window. But our goal will be, given this world coordinate system vertex, which pixel does it contribute to on this image window? And the way we do that is we're first going to change the entire coordinate system, first from world coordinate system to camera coordinate system, okay, CCS, so that the wherever the origin was in the original world coordinate system, your world coordinate system may be something really arbitrary. I mean, this may be origin, and this may be, I mean, your x-axis, y-axis. So we are going to change the addressing of in the entire set of vertices such that this point becomes origin, and this becomes our minus z-axis, and like whatever the up vector is. I mean, this is like a tilted image, but we are going to build a coordinate system around our camera and change the way when we do that. I mean, it seems like a very difficult thing to do. I mean, to do it or to change the address of the entire world, the entire virtual scene. But we are going to see that it's nothing but another kind of a transformation. When we have the modeling transformation, if you multiply this modeling transformation matrix with another matrix, let's call it V, or camera transformation matrix, let's call it C, for example. This is another 4x4 matrix. Okay, so this is a 4x4 matrix that moved, translated, rotated, or scaled the objects. And this C here is going to be our address changing transformation, which is nothing but another 4x4. So in terms of computational efficiency, if we multiply these two beforehand, if you have tens of thousands of vertices, changing their addresses is not so difficult than just making modeling transformations. Actually, you can, since matrix multiplication is associative, you can combine these two together again as a composite transformation matrix and do everything in one shot. And finally, another good thing is that after we change this address, to find its pixel coordinate, again we are going to multiply this with a projection transformation matrix, which is another 4x4 matrix. So the entire pipeline, the entire problem of finding which vertex, given a world coordinate vertex, given a model vertex, which pixel it's going to contribute to, its pixel coordinate, we'll be able to find it by just multiplying that vertex coordinate, let's call it Vi, with some matrix. Okay, we are going to multiply it with a 4x4 matrix. This is a 4x1 column vector. With this multiplication, we'll be able to solve this entire problem, which pixel it corresponds to. Then the problem of rendering will be just this. If you know for example, if you have a triangle, if you have its vertices, if you know which pixels these vertices project onto, then the rest is just painting inside of the triangle. I mean, if you know the colors, if you also compute the colors of these vertices by taking into account shading models like ambient, diffuse, and specular, again, if you know the colors of these vertices, what you could do is you can interpolate the color within the triangle to perform this. So the rest is just rasterization, which we call this rasterization step, is just interpolating the computed color at the vertices are cleared like this, and we just paint triangles. This is how we solve the problem. One thing that is not solved implicitly is that, for example, if you have a triangle that is behind this this cube here, if you just, starting from the object, as you can see, we do not solve the problem of which object is behind which object, because the triangle vertices that are behind this cube are also going to project onto certain pixels, which may be we actually lose after this projection. We don't know who is in front of who. And also this, if you just have the vertices, look at this, if you have this algorithm, you have the vertices of a square, just fill in the entire contents of that. If we change, for example, this is a blue cube, we draw it like this. So after you have its coordinates, you just paint the insides. If we do something like this, whoever you paint later is going to be painted on top of the previous pixel values, right? So we have to have a mechanism to figure out which object is in front, which object is behind. I mean, the ray tracing algorithm had this implicitly. By keeping track of T-min, we were actually finding the intersection with this ray that is closest to the image window. But there is no intersection of objects or anything in this new algorithm. We just have a vertex, which pixel it project onto, then paint, fill in inside of the triangles that between these pixel coordinates. No in front, back whatsoever. So in order to solve that, we are going to have we'll have to explicitly code something which is called the depth buffering. We are going to use, actually it's very similar to the idea of T-min. While we are painting these things, we are going to keep a different image of the same size, in which we are going to write what is the distance of the closest object that changed the pixel value. If we are going to paint a different object, we are going to take a look at the current pixel's depth. We are going to update the pixel color and the depth only if the new depth is smaller than the previous depth. So we are going to come to that later. Okay, so it's not part of this weaving transformations set of slides. So we are going to come to that later, but I'm just completely giving you the entire algorithm. Today, we're just going to see this first part, the camera transformation and projection transformation, which will get after we have the new addresses of these. They are still here. They just have new coordinates. How can we just make them find the pixel coordinates on an image window? Today, we are going to see how we can do that. The first part is not so difficult, and it's not so different than modeling transformations, the camera transformation part. Let me first talk about this problem. So the goal is, given an arbitrary camera position like this E and arbitrary camera vectors, we will be given U, V, and W. So we are given a new coordinate system. This may be a camera coordinate system or a different coordinate system. Our goal will be to figure out the new coordinates of these points in this new coordinate system. Remember the example we did last time where we were doing something in a 2D plane, and what we did was, in order to perform this transformation, the transformation that aligns the camera coordinate system onto the world coordinate system gives us a modeling transformation to change the addresses of the objects from world coordinate system to camera coordinate system. So it's like a little bit counterintuitive. It's like we are doing something, the reverse thing. If your goal is to move this one to move its addresses to this one, why don't we move the world coordinate system to this, you may think. But let's try what will happen. I mean, if we do that, let's again take a look at this simple example where this is 0, 0. I'm going to do something really simple. which is they have exactly the same orientation. So this is the new coordinate system x prime, y prime. This is the original coordinate system xx, and let this point be, for example, 4, 3. The only different thing is, I mean, they have the same vectors, 1, 0, 0, 1, but its origin is at 4, 3. Now, look at an object, look at a point that has a coordinate of 5, 4. Okay, if this object has if this point has a coordinate of 5, 4 in the world coordinate system, you can clearly see that in the new coordinate system, it's going to be, so its coordinate is 5, 4 in the world coordinate system. In the camera coordinate system, in the new camera coordinate system, as you can see, it's 1, 1, right? Oh, yeah, thank you for reminding that. Yeah, it's recording. Yeah. So thank you, site. Yeah, we are currently recording, but yeah, thanks a lot for the reminder. So let's get back to this one. So you see in the camera coordinate system, it's 1, 1, right? So what is the, I told you that in order to find this 1, 1, without actually thinking, without multiplying this 5, 4, 5, 4, 1 with this, we are going to find the matrix such that when we multiply it with this, we are going to get our new coordinate 1, 1, 1. So the problem is clear, right? Now, if we were to, so this is the world coordinate system, this is the camera coordinate system. If your goal is to move from world coordinate to camera coordinate system, you may ask, why don't we move world to this camera? How can you, what is the transformation to do that? To move world to camera, which is, I again warn you that this is not the correct way to do that, but I just want to show you that it will not work correctly. So in order to align world coordinate to on the camera coordinate system, you have to move the world to this 4, 3. So it's going to be a matrix that looks like this, right? 4, 0, 1, 3, 0, 0, 1. So it's just translation. Move 0, 0 to 4, 3. World coordinate is aligned with that. But what will happen if you apply it to 5, 4, 1? It's just translation, right? It's going to be 9, 7, and 1. Is this the correct? Is this point correctly in this new coordinate system? Does it seem like its coordinates? Coordinates should be 9, 7, 1? No. Okay, so this is not correct. So I mean, this simple example, if you forget whether we were aligning world to camera or camera to world, just think about this example. The correct solution will be, if you want to move from world coordinate system to camera coordinate system, you form the necessary transformation to align the camera onto the world, because you want your camera to be the new world. So you align, so that's another intuitive way of looking at that. You want the new camera system to be your new world coordinate system, so let's align the camera onto the world coordinate system, which will give you the correct transformation matrix, which is 1, 0, minus 4, 0, 1, minus 3, and 0, 0, 1. And if you apply it to 5, 4, 1 this time, you get, as 5 is translated by minus 1, minus 4, and minus 3, so you get the correct 1, 1, 1. You see, so we are aligning the camera coordinate system onto the world. So when we're doing it in 3 dimensions, if you remember the orthonormal basis alternative way to do the rotations, this alignment is going to be very simple actually, which is going to be composed of 2 things. First, move point E. We are going to have a translation which is going to move point E onto the origin, which is going to have a form like this: 1, 0, 0, minus EX, 0, 1, 0, minus E dot Y, 0, 0, 1, minus E dot Z, 0, 0, 0, 1. So what does this translation do? It moves first the camera I vector so that it's now at the origin. So we are going to have U, V, and W. after this transformation. The next transformation is what we need is some kind of a rotation, so that U is now aligned with this, V is now aligned with this, and that rotation can be done in one step if this U, V, and W are given, since these are coordinate systems of this and they are given as orthonormal basis vectors. All you need to do is this R is simply Ux, Uy, Uz, 0, and this is all 0, 0, 1, 0, 0, 0, 1, and Vx, Vy, Vz, Wx, Wy, Wz. So that's it. So if you multiply these two things, you get the transformation matrix, which is going to change your world coordinates to camera coordinates. So the camera transformation is this simple. But if you have any questions, anything that is not clear, please let me know. Please feel free to interrupt me anytime. Okay, so yeah, this is so we are going to align everything such that this UV W aligns with XYZ, and be first to transformation, and then this rotation by using this orthonormal basis matrix, and that's it. This is the, if you multiply this with this, the multiplication gives you this. You don't need to memorize these matrices at all, but just know that this is just a multiplication of these two. And that's the first part of the viewing transformation, the camera transformation. We are done with it. It's complete now. When the points are multiplied with this matrix, when you have any vertex over world coordinate system object, when you multiply this matrix, the resulting coordinates will be with respect to the UVWE coordinate system, which is the camera coordinate system. And this will make your camera at 0, 0, 0, and you're looking at -1. And now at this point you may ask, why didn't we tell this method before ray generation and ray tracing, right? I mean, if you applied this matrix multiplication to all of your vertices before you do the ray tracing, the ray generation function will be extremely simple, right? I mean, you don't need to do this complicated vector operations because your gaze is at -1. The z coordinates of all your pixels will be exactly at -d, where d is the distance of the image window to point E, right? Your camera is at 0, 0, 0 after these transformations. Actually, such a thing could be done. I don't know whether it's going to be more efficient or not, because those, I mean, in terms of mathematic derivation, finding the rays seems like a more difficult problem than it is after the camera transformation. But whether computationally it's going to be more efficient or not, I think we should either do some analysis on paper or let's pragmatically implement this one before change your ray tracing, ray generate function with this easier one to see whether it's really more efficient or not. Okay, so camera transformation is this. Do you have any questions? Then I'm going to now move on to the difficult part, because after this we have the viewport transformation, which is the easiest part, because in viewport transformation we're just moving from continuous space to image coordinates, which we have the image resolution now taken into account. But at this point in projection transformation, we don't have the image, we have this image window, but we don't think about the boundaries of this image window yet. We are thinking about the front and backward boundaries. Actually, we are thinking about the boundaries, but let's see how I'm going to show you. It's still in continuous space, not that discrete space. So projection transformation, there are two most commonly used transformations. Our goal will be, let me get back to this. Our goal will be to find, let me change this color, it's not very good. Let me change to black. So this is a really difficult transform. It's not a affine transformation, it's not linear. Our goal will be, given an XYZ value here, like this, our goal will be this, to find this XP, YP, and ZP, which is, for example, if this E is given, and if the gaze is everything is given, for example, to us, when this point, if this is the ray that passes through the image window, and this is the vertex that it hits, our goal will be to find this XP, YP, ZP, not by generating a ray. Actually, we could have, the problem is like this, right? If we could have, the ray generation is easy, right? We can have a ray equation that says E plus, let's call this point V, this XYZ, E plus V minus ET. So I could have, I mean, both the points, and actually this E is 0 right now. That's also, you know that, right? Because in this at this point, while we're working on projection transformation, we now can assume that the camera transformation has already been performed. So this point E actually is now on my new 0, 0, 0. Okay, so from 0, 0, 0 to this vertex V, I'm going to have my ray equation as RT is equal to simply VT, because E is 0, therefore this is my ray equation, whatever the vertex coordinates are. Now, the problem of finding this XP, YP, ZP now boils down to finding the intersection of this ray with the image plane, image window, and then this intersection point will be my XP, YP, ZP. So that's actually, we'll try to find that intersection point. But here, what we are trying to solve is that, can we find this intersection? We are going to find this intersection with an equation, but can we turn it into another matrix multiplication in such a way that, let's call this projection matrix, MP. If I multiply this V, this XYZ, can I find this XPYPZP correctly? XPYPZP1. Okay, can we find such a projection matrix? And when we derive the equation of this intersection, we'll see that this transformation, unfortunately, is not linear. It's going to be something like this. XP, we'll find XP is going to be equal to X divided by minus Z, for example. It's going to be something like this. And you cannot do that. You cannot have a matrix here in such a way that I mean, look at this first row where you multiply it with XYZ. In order to find XP, the equation format is like this. XP is equal to A times X plus B times Y. So it's linear. C times Z plus D. So with such constants A, B, C, D, which should not depend on X, Y, Z, okay, it's not possible to have an equation of the form like this. But what we will do is, we are not going to directly get XP, YP, ZP like this, but what if, after I multiply it with this, I get a vector which is something like this, X and the fourth component, for example, what if I have this XYZ and divided by minus Z? If I have it like this, maybe ignore the last one first, because the Z coordinates, the image window here, we are only going to interested in XP, YP coordinates. Now it's a 2D window, right? It's Z coordinate. We are going to, we'll maintain these, we'll maintain the depth, but if I multiply my XYZ with a projection matrix, if I obtain something which is of the form like this, which is possible to do, right? I mean, here in this homogeneous coordinates, the last coordinate is not 1 anymore. And in other words, if you want to go to three-dimensional coordinate system, the way to do was, from homogeneous coordinate to regular coordinates, divide everything by the homogeneous coordinate. So your x coordinate is like this xh divided by this h, whatever it is. So exactly, so as you can see, this is how the fourth value, by setting it to minus z, I will be able to generate equations that look like this. So that's the thing that we will be doing in projection transformation. Now, there are we haven't seen orthographic parallel projection yet. Orthographic parallel projection is like a degenerate case of ray tracing in which where the eye point is at infinity. If we had the eye at infinity, infinite distance from the image plane, all the rays that are emerging from the eye will be parallel to each other. So when the rays are parallel to each other, this is called orthographic projection. And in this orthographic projection, the objects that are far away, they do not appear smaller. Everything is going to project it, whatever their size is in the real world, they're going to be projected to exactly the same size on the image window. And such orthographic projections are sometimes used in mechanical drawings, computer-aided design, because the perspective distortion sometimes may make objects seem, for example, distorted, smaller at the end. And if you're looking at them very closely, it may give you a feeling that they are not really cubes or they are not really rectangular prisms. In mechanical drawings or computer-aided design, orthographic projection may be the preferred way to visualize things. And perspective projection is what we are familiar with from ray tracing. We have a central projection, and light rays actually diminish. The light rays focus on this center of projection. In this projection, faraway objects are projected onto smaller areas on the image plane. So what are we going to do this in this orthographic projection? Orthographic projection actually is, if we were to do it, again, I'm going to show you something. Imagine we are looking at our image window from the side, okay? So this is where E is, okay? Now I have X, Y, Z here some point, and my image window is equal at, for example, Z is equal to -2. Everything here should have negative Z values, because if the things that I see lie in negative Z space, because my camera is at 0, 0, 0, and my gaze is at 0, my gaze vector is 0, 0, -1. Okay, imagine you have an image plane at Z is equal to -2, and we are looking at it from the side. Now, if we have parallel rays in orthographic projection, if all the rays are parallel to each other, to this image window like this, orthographic projection becomes something very easy, right? I mean, you may immediately know, for example, if you have X, Y, Z, which coordinate is going to be projected on this image window? What is XP, YP, ZP? Okay, so since everything is parallel to each other, the XY coordinates actually do not change, right? XP is equal to X, YP is equal to Y, and ZP is equal to, is it equal to ZP? No. ZP is equal to Z? No, ZP is equal to -2. So everything is projected such that, I mean, the projection of any point here onto the image plane is in such a way that their XY coordinates, this image plane is parallel to the XY plane. So if your rays are orthogonal to this, the projection of any point here, it will have the same XY coordinate on the image plane. So orthographic projection is actually something very easy. Your X and Y coordinates do not change, and your Z coordinate, every pixel is going to have a Z coordinate of -2. But if we do projection like this, convert everything to -2 here, we lose the depth of the objects. For example, if you have a triangle, if you have a rectangle here and there's a triangle behind it, their vertices are going to be projected onto same Z, so depth information will be lost. So during this projection, what we may want to retain is that we may want to retain this depth information, because we'll need to use it later, saying that which object is in front of which other object. So this depth information we need to retain. We are not trying to solve literally a projection problem in which everything projected is going to have this, is going to be projected with to the plane z is equal to -2. So this point's coordinate may be xy -2, but I'm not all interested in the coordinate of this point on the image plane. I need some information like the front-back information so that I will use them later, as I said. But this xy coordinate, the 2D coordinate, is something that I'm looking for, which will tell me that it's pixel coordinates on the image plane. But this third dimension, which is everything projected here, will have the same z value. I can use this third dimension to actually retain. Instead of having -2 here, I can also say zp is equal to z like this, to retain everything. So orthographic projection doesn't do anything. You can have an orthographic projection that looks like this. If you want to return the original z, maybe just you may want to invert it because it has negative values. If you want to show that show this z value to indicate its distance from the image window, what you can do is actually distance from the image window is going to be something like this. We are going to add -2 to that, right? So look at this orthographic projection matrix. The last row is 0, 0, 1 here. So everything remains the same. The last coordinate becomes -z -2, right? So -z -2 makes it whatever your z coordinates were after the projection. This here, this value here, shows the distance of the point to image plane. If you have a projection matrix that is like this 1, 0, 0, xy doesn't change, they're exactly as they are, and the last coordinate is inverted, and the distance from the eye to the image plane is subtracted from that. So therefore, it's not the distance to the origin, but it becomes distance to the image window. So this is really simple, but what we are going to do something additional in orthographic projection. It's like for standardization of different coordinate systems, we are going to something called this canonical viewing volume. This canonical viewing volume means that it's a viewing volume that is going to be understood same in every graphics processor unit. So this canonical, you can understand it as a standardized viewing volume, regardless of your units in the world coordinate system, or normalized viewing volume. You can say this normalized viewing volume, standardized canonical viewing volume. So what it does is, in this orthographic projection, what we want to do is we want to project everything, we want to transform everything inside a cube of, I think this is a 2 by 2 cube, it's not a unit cube. Everything is going to be transformed into new coordinates such that the closest of by the way, look at this. What is this rectangular prism doing here in this orthographic projection? So we know that our image plane has some boundaries, right? We don't want to project, I mean, when we're projecting things, our image, if you remember, in ray tracing, we had this LR bottom top boundaries. Okay, so everything, for example, this was from -2 to 2, this was from -1 to 1. We had this rectangle, we were seeing everything inside this image window. So it had boundaries, two-dimensional boundaries. Now, in addition to, so this side, and which is equal to the boundaries on this side actually, refers to exactly those same boundaries. If you look at this is your eye point, you're looking in this direction. This, let me try annotate, this window that you see here is your previous image window. And this was its distance. This was D. Okay, this is your previous image window. Now, what we also define is that we define a far image window. We call this the near plane, near image plane, and we call this one the far plane. We are going to want to define a viewing volume inside the virtual world are seen, so that everything inside this viewing volume is going to be visualized. We didn't necessarily do this. What we will not be seeing in ray tracing was actually again something implicit. When we shot our rays, imagine these rays that pass through the corners. Anything, and if you had an object outside this uh, pyramid, you're not going to see them, right? So similar to that, we're also cutting this pyramid from the far side. In this orthographic projection, we have now 6 parameters. In addition to left, right, bottom, and top, we also give 2 new parameters, minus n and minus f. This is the n and f. We can call this n and f in positive, actually, but the image window is at z is equal to minus n, and this minus n was also a parameter actually in ray tracing. It was the distance of the image window to your, so it's that distance d parameter. D parameter corresponds to this n, so you have your image plane at z is equal to minus n. But as I said, we have an additional parameter here, which is the far plane. This far plane is like the farthest distance that you want to see the objects. If the objects are further away than this distance, you don't want to visualize them. This far plane has some strange effects, especially in games, for example. Sometimes this, in very early games in 1990s, maybe at the beginning of 2000s, you may see that there's no building out there, but as your character moves towards the building, it appears like out of thin air. So because it's now closer than the far plane, that's why you're able to see it immediately. So it's really unrealistic, actually. It's not this far plane idea is not realistic, but it's for efficiency and just to cut out, to prune objects that are very far away. This is something that people decided to employ, the far plane. Now, orthographic projection, in addition to being the very simple, we have seen orthographic projection here in this slide is something very simple, right? I mean, look at this matrix. Instead of just keeping the points like these, what we are going to do is we are going to perform a transformation such that this arbitrary viewing volume, I call it arbitrary because this LB minus NRT minus F, these are just dependent on users' inputs, the parameters in our world coordinate system. Our projection is also going to take care of the normalization step, such that this rectangular prism here is going to be turned into this cube, in which everything is, all the coordinates are between -1 and 1 now. By doing this, we can perform something called clipping or pruning of objects that are outside. We can just say, if for example, after this transformation, if you have objects which are entirely outside this cube, which may be very easy to figure that out by comparing it the standardized -1, -1. I mean, if you're going to have your if conditions, you can just have them compared against this -1, 1. We can just forget about objects that are outside this canonical viewing volume and not try to render them at all, which is going to increase our efficiency a lot. So that's the one thing we do in orthographic projection: convert everything to this standardized viewing volume. So, I mean, if there are objects that are outside here, after the orthographic transformation, they're still going to be transformed outside here, but their coordinates will be, for example, its y coordinates will be greater than 1 if it's something outside 1. But anything, if any vertex inside this arbitrary orthographic viewing rectangle is going to have coordinates strictly between -1, 1, 1 and 1, 1, 1. Okay, so its coordinates, its x values, y values, z values will be strictly between those after this projection. So how do we perform this projection then? And oh, there's also something interesting here. Not only if you look at the coordinate system here, it's z coordinate. I mean, if this is from -1, -1, -1, so this should be 1, and this should be -1 in the regular right-handed coordinate system. The coordinate system is also inverted in such a way that actually it's like a mirror coordinate system in which the z coordinate is now increasing in positive direction from the I point. Okay, so it's turned into now the z values become like distances from the camera after this is done. And here is the transformation matrix that is going to establish that. So we need to map this LB minus N RTF to -1, -1, -1, these to 1, 1, 1. This is just, I mean, all these, we can actually treat all of the coordinate axes separately as if they're independent from each other, because all the coordinate axes are normalized irrespective of the other ones. So if you look at a problem like this, so how did we come up with this matrix? Let me show you the equation. So our goal is to do something like this. So imagine we are looking at from the front, where we have this as L, this is R, okay, L and R here. I have a coordinate that is somewhere here. Let's call it X. Okay. Now I want this to be -1, this to be 1. Now what should the new XP be in this? Okay. What is XP? Such that it's between -1 and 1, and it is exactly the same position. I mean, when this L turns to -1, this R turns to 1, it has to be exactly on the same spot as X. So what should XP be in that regard? So what we need to do is, we need to just say, first of all, whatever the distance was, which was R minus L, right? Now the distance is 2, so the X should be scaled with this amount, 2 divided by minus R, 2 divided by R minus L, because whatever the previous distance D was, it's now going to be a distance of 2, and this previous distance D is just given by R minus L. So everything, the scaling, the stretching of the coordinates that are in this line is basically 2 divided by R minus L. And or you could find it also like this. Your new coordinate should be -1, so we can do it like this. Here the distance between X minus L divided by R minus L should be the same as XP minus -1 R and 1 minus -1, right? We can also have an equation like this. Is this correct? I just intuitively wrote this one to figure out how we can find XP given X, L, and R. Do you see anything wrong with this equation? So what I tried to do was X minus L divided by R minus L. So the ratio of this distance to overall this distance should be equal to, if I want XP in the same location, the distance of XP to -1, and then this new coordinate is 1, the distance of 1 to -1, which is 2. So I think if we take XP out from here, so let's try to simplify this a little bit. X minus L, R minus L, then XP plus 1 divided by 2. Now, so this is 1 over 2. So all I need to do is multiply this side by 2. If I do that, 2x minus L, oh, this is L, x minus L divided R minus L is equal to XP plus 1, right? And then put this minus here. XP is equal to 2x minus L divided by R minus L plus 1. Now, arrange this part in such a way that constants are, I want to arrange this part so that it becomes something like this, ax plus b, okay, whatever the coefficients of x are. With the coefficients of x, as you can see, 2 divided by r minus l, right? So it's going to be something like this, xb is equal to, oh yeah, thank you, this is going to be minus 1. Okay, thanks a lot for that. So, but the coefficients of x are xp is equal to 2 divided by r minus l x. Okay, then I have here, what do I have here? Minus 2l divided by r minus l. Okay, so minus 2l divided by r minus l and plus, minus 1. This minus 1, I can write it as L minus R divided by R minus L, right? So L minus R divided by R, So this is going to be minus 2L, this is plus L, so it's going to be R, it's like minus R plus L divided by R minus L. It should be something like this B. So this is the translation part. This is the, so if you go back to this, actually it's exactly what we found, like minus R plus L divided by R minus L. This is that B part that we have found. Yeah, so I have found this one correctly, this part of the equation, and 2 divided by R minus L, we find that one also correctly. So this is exactly, this formula that you see here is exactly coming from this simple, let me triple star it, so this simple equation with one unknown only, xb. Okay, so this is just linear normalization with respect to this. So after this becomes your orthographic projection. All right. Now, let's have a 10-minute break before we continue. The orthographic projection is therefore very simple. It's actually the main thing that it's doing is normalization to the canonical viewing volume, because the orthographic projection itself is very easy. The original xy coordinates are retained. So therefore, what it's actually doing is mapping to this canonical view volume. We have this rectangular prism converted to this cube of size 2 at each side, and this is our orthographic projection. And we are going to be using this, as I said, for normalization. And now we're going to next talk about perspective projection, but let's have a 10-minute break, and we are going to continue at 10:45. I'm going to stop recording now.